In this lecture, we will discuss the optimum receiver in additive wide Gaussian noise channel. So we already discussed the matched filter, earlier in the previous lecture, the matched filter. So let me discuss this optimum receiver, which of course has a matched filter, which is the matched filter receiver, and we will see the maximum likelihood decision, the maximum likelihood decision, the maximum likelihood decision, maximum likelihood detection. We would see the maximum likelihood detection process at the receiver. So just to recall my previous lecture, let me use few minutes to recall what we have done in the last lecture, and then we will continue from there because we need that knowledge today. So if you go back to your previous video, what actually we did, we selected two orthogonal waveforms, S0 of t and S1 of t. Right, we selected these waveforms and we said that we have a pulse from 0 to t, or you can say tb, with a magnitude plus a. Similarly, we have another waveform which is S1 of t, and it is orthogonal to this orthogonal to S0 of t, and it also exists from 0 to tb, and it has the this wave shape, which is given here in this S1 of t, is shown as S1 of t. We then derived the matched filter response for H0 of t. We actually just said that H0 of t is the if we observe H0 of t, that is the time shift, the actually time inversion, and the scaled, the delayed version, time inverted and delayed version of the S0 of t. So your matched filter for S0 of t is actually H0 of t, and if you again plot this one for this particular S0, it appears to be the same. If you invert it and then delay it by the TB, you would get the same result, right? So our H0 of t appears to be this one. Similarly, H1 of t would be the matched filter response for S1 of t, and that is again the time inverted and delayed version of S1 of t, and it would appear the time inverted and delayed version appears to be like this. So it actually exists from 0 to tb on the time axis with a plus a magnitude and a minus a peak amplitude. The peak amplitude plus a and minus a. In the first half period, it is minus a. So this is H1 of t and H0 of t. These are the matched filter responses which we tried earlier in our previous lecture. And then we also saw the signal outputs of the matched filter when S0 is transmitted. So we saw that if we transmit S0, keep this assumption in mind, that if S0 is transmitted, because you can also proceed by assuming that S1 is transmitted. So when S0 is transmitted, we said that our received signal, which actually our receiver looks like this. We have two matched filters, H1 of t and H0 of t. H0 is the response is matched to S0, and H1 the response is matched to S1. So when our received signal now we discussed this in my previous lecture, we discussed our signal in the absence of noise, right? Actually our received signal is when we discuss the transmission, our received signal, when we say S0 is transmitted, then the received signal is actually equal to S0 of t plus N of t. But we discussed the performance in the absence of noise, which means we assume that this is 0, so the received signal is same as the one you transmitted. So if this is the case and you pass this R of t through the upper branch and the lower branch, and you take some output from these filters, and you take those outputs at instant, you observe those output at instant TB, you get two sample values from these two branches, right? And actually the output of these matched filter, we already in the absence of noise, we said that we have already drawn these outputs, and in my previous lecture, those who have not gone through it, just go through those lectures, right? And we said that the output of the first filter, this is Y0 of t, the output from the upper branch, which is Y0 of t, would appear in this form, which is the peak value is actually at instant TB, and the whole response is up to 2 times TB bit interval. This peak value is actually equal to, a square times TB, So if you take I guess we took the unit time TB equal to 1 and A equal to 1, and we got this one. If this is other than 1 values, then it would be A square TB, which you can prove easily. Similarly, we also saw the output of this y1 of t. We also saw the output y1 of t from the second branch, the output of the matched filter when S0 is transmitted. Keep this in mind. We are talking about the S0. We assuming that transmitter has transmitted S0. So when it passes through the matched filter, the response for instant from 0 to 2b instant, we get this response, and it is 0 at instant TB, right? And this peak value is actually equal to A square TB over 2. Similarly, its negative value would appear here. So the response here at this instant is, in the absence of noise, it is when we transmit S0 and we observe the response of these two filters, the matched filters Y0 of t and Y1 of t, it is the response of the first one is maximum at this instant TB. So when we sample it at this instant R0, we expect R0, which is maximum, right? A square times TB, and we expect R1, which is 0. We expect R1, which is 0, which is the output, Y1, which is the sample value at t equal to TB from the second branch, and R1 we expect equal to 0. Now, if the noise is not 0 here, if this term is not 0, this noise term is not 0, if it is present, it means we still would sample our signal at t equal to TB, but we may get a distorted waveform which may look something like this, which may be some distorted waveform, right? We would get some value, but that value would not be exactly equal to A square TB. We will see now in a short while what this value actually looks like. We actually derive the expression for this one in case of noise. Similarly, the noisy signal here would be a distorted one, right? It would be a distorted one, and you may not get exactly 0 value. So it may be a distorted waveform. So you would get some value other than 0, which it means that when the noise is there, in the absence of noise, we have a very good waveforms, clear waveforms. But when the noise is there, we get some value. Value R naught is not exactly equal to the energy of the signal, but there is another term which is N, noise, and we derive these values. We say N naught and this is N1. We say that in the presence of noise, we actually have these values E plus N naught and another value which is actually E plus which is just the R1 is equal to the noise value. This N naught and N1 are zero mean Gaussian, right? This N naught and N1 we say that these are zero mean Gaussian. When we say, now we know the mean but we don't know the variance, right? We have to find the variance of these terms, because the variance with the variance we have the signal energy, and the noise variance would give us the noise energy. So that is why we are interested in the variance of these components which are present at the sampling instant. So and at the sampling instant, R naught, when you transmit here, we assume that we transmit S naught. When we transmit S naught of t, we get R naught and R1, two sample values, and our detector has to take decision. It has to decide whether S naught is received or S1 is received. Now it would decide with the help of these two values. So we expect, as a matter of fact, we expect that R naught is greater than R1, because this is this just generally speaking, the energy of the signal, it's quite high. We have a strong signal usually we send from the transmitter, and the noise value, the noise term is also there, but this noise term is present in R1 as well, at the output of these R naught and R1, which are the two outputs, the sample value. So it is always there. So we expect that the sum of these two numbers is greater than the sum of this one, which means usually our detector would expect that R naught is greater than R1. And if it finds R naught greater than R1, then because now H naught of t is the matched filter in the upper branch, it means that the matched filter is actually, it's matching the received signal with the with S naught, and the lower branch H1 of t is matching the received signal with S1. So these values R naught and R1, these measures the correlation, you can say. It measures the correlation of the received signal with S naught and S1, because initially we started our procedure by assuming that S naught is transmitted, and we got our receiver gave us R naught, which is the energy of the signal, plus N naught. We derived the expression for this one in the previous video, and for R1 as well in the previous video. So we usually expect that R naught is greater than R1, and if it finds that R naught is greater than R1, then the detector, based on these two values R naught and R1, it would decide that S naught is transmitted, right? It would decide that S naught is transmitted, because the upper branch, which is matching the received signal R of t, the received signal R of t with as the R of t with S naught of t, or H naught of t gives us that measure. So it's matching the received signal with S naught of t. It finds that this matching is higher than the matching in the lower branch, so it decides in favor of S naught. This is the way the receiver detects the signals, right? So if R0 is found to be greater than R1, S0 is detected correctly and the receiver takes correct decision. However, it's possible. It means now the probability of this event, the probability of this event that R0 is greater than R1, because we have this random numbers are involved here. Random Gaussian process is zero mean Gaussian process. Zero mean Gaussian numbers are here. Sample values, right? Zero mean Gaussian values are here. So the probability that R0 greater than R1 contribute to the probability of correct decision. So this is actually the probability of correct decision. But it's also possible that R1 becomes greater than R0 if this noise is if the signal you receive is a very low energy signal and the noise N1 is greater, and this sum becomes less than this N1. So in that case R1 would become greater than R0, although its possibility is low, but still if it happens that R1 is greater than R0 and the transmitter has actually transmitted S0 of t, then the receiver would say, if it is found R1 is greater than R0 is found, the receiver would say that S1 is transmitted, and actually the transmitter has transmitted S0. So the receiver said that S1 is received. So this is a wrong decision. So it means the probability of this event, probability that R1 is greater than R0 when S0 is transmitted, would contribute, it would make the probability of error. It would give you the error probability. So we are interested in finding out the mathematical expression for this error probability in terms of the energy of the signal and the noise, the energy of the noise, right? So we are interested in finding out. So we will be using this expression as the base for finding out that the expression for probability. So let's continue from here. Okay, let's continue from here, and we try to use this expression to find out the probability. Now let me specifically write this N0 and N1 as well. So what we said that our probability of error is actually the probability that R1 is found to be greater than R0 given that S0 is transmitted. Given that, keep this in mind, this assumption, because if you say that S1 is transmitted, you start your derivation with S1 and you try to find out the probability error, you would get some other expression. Ultimately the result would be same, but the expressions and the logical reasoning would be a bit different. So this is the probability of error, probability that R1, the sampled output at the second branch R1, is greater than R0, the sampled output at the upper branch from the mesh filter receiver. It is found to be greater. So now if we substitute those values, it means that N1 is greater than the energy of the signal plus N0, right? And if we further write it just using our basic maths, it is N1 minus N0 is greater than E. This makes the probability of error. Now N0 and N1, we say that N0 and N1 are zero mean Gaussian. N0 and N1 are zero mean Gaussian. It is already mentioned in our text that okay, our N1 and N0 is zero mean Gaussian process. Now if it is Gaussian, it means the difference of these two is also Gaussian. The difference of these two is also Gaussian, right? So for if n1, n0, n0 and n1 are zero mean Gaussian. These are zero mean Gaussian processes. So the difference, which we can denote by n1 minus n0, this is also zero mean Gaussian, right? The difference is also zero mean Gaussian. Now if this process is zero mean Gaussian, we are interested in finding out that this the zero mean Gaussian this difference is greater than the energy of the signal. Now if this difference is greater than the energy, we are actually interested in finding out the variance of this variable n. We are interested in finding out the variance of this variable n. Why the variance of this variable n? Because it is a zero mean Gaussian process, and the variance of a zero mean Gaussian is actually its energy, the variance. So we are interested in finding out whether the energy of this n1 minus n0 is greater than the energy of the signal or not. So this is what we want to know, that whether the energy, the energy of this noise term is greater or lower, right? So let's try to find out this energy, the variance. So the variance is actually equal to the second, for a zero mean Gaussian process. For a zero mean Gaussian process, the second moment, which is defined as the expected value of the square of the random variable, the expected value of the square of the random variable. So the second moment, we would like to find out this second moment, and this is actually equal to the variance of the this is actually equal to the variance of the noise. This is actually equal to the variance of the noise. This is from your basic knowledge of the probability and random variables, right? So if you have a zero mean Gaussian process, its second moment is actually equal to its variance. So let me find out this second moment, and we can rewrite it as the expected value of n1 minus n0 whole square, right? So if you solve it further, you can write it as the expected value of n1 square plus n0 square minus 2 times n1 n0, right? And if you write this expression, if you further write this expression, this expectation operation will operate on the first variable, the second random variable, and 2 times the expected value of n1 and n0, right? So this is you can rewrite this expression in this form. Now let's try to find out the this n1 and n0. Let's try to find out this term first, and then we will come to the other two terms as well. So let me find out this term. So you are familiar with the n0 and n1. In our previous lecture, we said that n0 is actually equal to 0 to tv. It is s0 of t, and the noise, this integral, this is the noise, right? And similarly, we have expression for n1, which is 0 to tv s1 of t and noise. This integral is n1. So when we say n0 and n1, the product, actually we need to multiply these two, right? So multiply these two expressions, and you would get n0, which is 0 to tb. Now I would use a different variable, tau, for the second. So here I would use tau variable, tau, right? instead of t, I would use tau variable for the multiplication. So you can say t is equal to tau, right? It's the same just a change of variable to facilitate this analysis. So this product can be written as 0 to t s naught of t, and I would write s1 of tau and n of t, and then n of tau, and we have d dt. Let me write dt, d dt, and d tau, right? So we have just I have just written this product. There should be one more integral here. I have written this product now into n naught multiplied by n1, but we need to take its expected value, right? So let's take its expected value. So if I write the expectation operation here, the expectation operation, if I write the expectation operation, the expected value here, I would have to write it here, right? The expected value. So now let's take this expectation and we write the expression. We write our expression, the right hand side. Now the expectation would only this S0 and S1 are deterministic signal. You can see these are the deterministic signal, fixed value. These are the random values. So expectation operation would run over the random variable. So we can rewrite our expression in this form: 0 to TB, 0 to TB, and S0 of T, and then we have S1 of tau, and my expectation operation, right? It would run on n of t, this expectation operation, and n of tau, now dt, and d tau, right? D tau. So this is our we can rewrite our expression here. Now keep in mind, this is important. This expectation operation is important. This is noise. This is also noise. Noise is independent. So if the noise is independent, their dot product, this is actually the n of t, n of tau. It would expected value. You would get the if you write it, you would get the it's just like a dot its expected value are it's very similar to the because you have expectation, right? So it's integral of n of t, any value expected of that variable is actually the similar to the dot product. So because the noise samples are always independent unless you discuss it for t equal to tau. So when you discuss it for t equal to tau, this is the square of the noise term, n square of t, you can say, or n square of tau. So the expected value of the square of the signal random process, it would give you the noise variance or the noise power spectral density, as I said that it is the noise power. So the noise power, this term here, if you go to the noise power spectral density, you can clearly see that this term is n0 over 2 and delta t minus tau, which means because these are two noise samples, so if they are taken at a different instance, then the product would be 0 if t is not equal to tau. If t is not equal to tau, this product would be 0. If t is equal to tau, it means we are talking about the same instant. So we can write it the square of this signal. It means the square, and the square is actually the square of the signal. Its expected value would give you the energy of the signal, and the energy of this signal and the energy of the noise from its power spectral density can be observed, which is equal to n naught over 2. So we can say n naught over 2 delta t minus tau, because it exists only when t is equal to tau, right? This delta t minus tau says that it exists only, it is there only when t is equal to tau. It is n naught over 2, otherwise it is 0. So now from here onward, when t is equal to tau, this expectation operation, this is equal to this thing. So let me put it this way. Let me rewrite this expression below by assuming that t is equal to tau, right? We are talking about the t equal to tau instant. So when t is equal to tau, it's simply n naught over 2, right? 0 to tb, and you have another integral 0 to tb, you have s naught of t, s1 of tau, and this is delta t minus tau dt d tau. This would exist only now with this delta function. Keep this in mind. This delta function, now this integral, the value would this integral would give you a value only at t equal to tau. Otherwise it is 0, because this function is 0 and it would make all the integral equal to 0, right? So just put t equal to tau, and when you, or in other words, let's try to integrate this one first. Let's try to integrate this delta of t equal to tau, right? So for t equal to tau, if you integrate this one delta t, you would get a unity. The integral of a delta function is unity. So putting t equal to tau, you integrate delta of t, and you would get only with one integral, which is s naught of t, or you can say tau, up to you, s1 of t, right? s1 of t, and you would be left with dt, because one integral here we get one. Integrating this delta t, we are just consuming this integral with delta t and use let's say d tau, right? Suppose d tau, right? D tau. So t equal to, if you substitute t equal to tau here, you would get 1 for this one. So the remaining part is this and this, which I just rewrite over here in this equation. Now this is nothing but the square of now these two, not the square actually, these two signals are orthogonal, s0 and s1. It means we would get 0. The integral of these signals are orthogonal, so we would get 0, right? So this is this is 0. This part is 0. So we conclude that in our expression you are trying to find out the expected value of n square. Now it is actually equal to expected value of n1 square, expected value of n naught square, and the third term becomes 0, right? The third term becomes 0. So we are not now only having n1, we need to find this expected value of n1 and n naught square. So generally speaking, let me find this one for you. Expected, we did it, but let me redo it. n1 square, n1 is s1 of t, n of t dt from 0 to tb, right? So we can write the n1 square as the double integral 0 to tb s1 t s1 tau n t and tau dt d tau, right? Let's change the variable of n1 and n1. So the square of n1 square can be written in this form as we did in the previous. It's the same procedure as we did in the previous derivation. So if you are interested in its expected value, you are interested actually in this expectation. So let me write this expectation here. If I rewrite this expectation, it is 0 to tb, 0 to tb, s1 t, s1 tau, the expected value of n of t, n of tau, dt, d tau. Now we already discussed that this is equal to n naught of t delta t minus tau. So we just replace it. Let's rewrite that value here. So you have double integral s1 t, s1 tau, and not, let me write this value here, and not to delta t minus tau, right, dt d tau. Now this only works here. We say it is from 0 to tb, 0 to tb. Now if we rewrite this expression, and not again, once again, and not over 2 would be here, and you can just solve this, you can just solve one integral, just we would be left with 1, putting t equal to tau. So this would be s1 t, and again here you are getting s1 of t from here and dt. One integral goes by integrating this term, right? So you have s1 square now. You have s1 square from 0 to tb is actually the energy of the signal s1, right? It's equal to the energy of the signal s1. The energy of the signal s1 and s naught is same. You can so we can rewrite that this is actually equal to the energy of n naught times E over 2. So this is the expected value. This is the this is actually the expected value. The expected value of n1 square is equal to expected value of n1 square is equal to n naught over 2 times E. Similarly, you can prove that the expected value of n naught square is equal to n naught E over 2. Now, if you see the expected value of n square, right? This is what we were interested in. It is actually equal to n naught times E over 2 plus n naught times E over 2, and the third term is 0. So we can rewrite this expected value. The expected value of n square is actually equal to, for orthogonal signal, it is actually equal to n naught times E. So this is the expected value of the n naught square, which is equal to the variance of the noise. As I said earlier, this is actually equal to the variance of the noise term. This is actually equal to the variance of the noise term. Now, once you take this variance of the noise term, and we are saying here, if you observe, this is the variance of the noise term. Now, if you go back to your mathematical expression, if you go back to the expression of the probability of error, we said that the error probability is actually equal to the probability that n is greater than E, right? And this n is 0 mean Gaussian. This n is normally distributed with mean 0 and variance sigma n square, which we just found. We found this variance, right? We just found this variance. So if our n is 0 mean Gaussian, the variance was unknown, which we just found, now we can find the expression for our error probability. It means we are talking about the noise PDF. Let me draw it graphically first. We are talking about the noise PDF, which is a bell-shaped PDF. It has a mean 0 and variance given by sigma n square, and we are interested in finding out if this is, suppose E, this point is E. We are interested to find out this area, which gives us the probability of error. This gives us the probability of error, right? This is from this expression. Your n is greater than E. So this is a random variable n, which is normally distributed. A random variable n, which is normally distributed, and it is greater than E. E is some value here, the energy, always positive, signal energy. So we have some positive point here, and we are interested in finding out the this probability. We are interested in finding out this probability. So we can write this. This is actually the probability of error, and you can see this is the right tail probability of the standard not the standard normal. It is the right tail probability of this the right tail probability of this random variable n, which is noise which is present in at our communication receiver. So it would be in the form of q of x. So you can write your expression now. You can write your expression for n. We already have its variance, and it is Gaussian. So the PDF of, let me write specifically the PDF of n. The PDF of n would be equal to 1 over 2 pi sigma n square e raised to the power minus n minus the mean value, which is 0, right? So n square, let me write n square over 2 times sigma n square. So this is the PDF of the noise. This is the PDF of the noise. We want to integrate this PDF from e to infinity. So that would give us the probability of error for our receiver. So let's try to integrate this PDF. We are interested in finding out the probability of error, which is to integrate p of n, from e onward to plus infinity. This is giving us the error probability, right, from e to infinity. So let's put this, substitute this value, and it would be from e to plus infinity 1 over 2 pi sigma square n, and e raised to the power minus n square over 2 sigma square n dn, right? So we need to find out this integral, which would give us the mathematical expression for the error probability. Now we want to represent, it is easy to represent this tail, because this is the right tail probability of this Gaussian curve. We would like to represent it in the form of q of x, and for that purpose we need here, now this is a very good point. It's point to be noted that you need this, you need to change the variable here used in this integral, which is n. Right, you need to change this variable n. So the change of variable should be such that it matches the q of x. Now let me rewrite q of x, and then I'll discuss it with you. What is q of x actually? If you write q of x, it is the PDF. It is the integral of the PDF 1 over under root 2 pi e raised to the power minus t square over 2 dt, and this is from x to plus infinity. So if you go to the lecture video which I uploaded for the q of x, your q of x is the integral of this standard normal PDF from x to infinity, right? This is the expression for q of x. Now if you observe this exponential term, in this exponential term, the here we have the square of the variable over 2, right? So we have to convert our expression, which is this expression p of e. We have to convert this expression in such a way, we have to change the variable of this integral in such a way that this exponential term becomes the square of the variable over 2, right? So this is our target now. So we have to choose such a variable that we can represent this. The rest would be okay. The rest would become, everything will be perfect then. Just change this variable in this integral in such a way that the exponential terms becomes the square of the variable over 2. So to do that, what we can do, we can choose the variable, let me use another variable y. We can choose a variable y which actually is equal to n over sigma n. So if we choose this variable to be y, then you can see that our this exponential term would become y square over 2, right? Y square over 2, because n square over sigma n square would become y square. So it would be the square of the variable over 2. So this change of variable would work. So let me choose this y here. If I choose y as n over sigma n, if I choose this y, we can choosing this y means I have to change the limits as well. So the limits for y, now we have the limits for n. The limits of n are given by, the limits of n are from e to plus infinity, from e to plus infinity. So the limits of y would be, when n is e, y is actually equal to e over sigma n, right? When n is e, y is equal to e over sigma n. And similarly we can say that for n equal to plus infinity, y would also be equal to plus infinity. So these are the limits of y which are taken from the limits of e and this expression. Now we can see that actually we can also write dy from here. We can write dy is equal to 1 over sigma n dn, right? So we would use these values. Now using this set, actually let me bring it here. Using this set, I can rewrite my integral for the probability of error. So if we go back and rewrite our integral for the probability of error, we can rewrite it in this form, that okay, our probability of error is actually equal to the probability of error is actually equal to 1 over under root 2 pi, right? And we have sigma square here, sigma n square, 1 over 2 pi sigma n square. Now from e to infinity means we have e over sigma n, right? We have e over sigma n. The instead of e, we have e over sigma n, e over sigma n to infinity, and then the exponential term is actually y square over 2, and instead of dy we can write the, instead of dn we can write sigma n times dy, right? Sigma n times dy. Now this is we have changed the variable. Now you can see that its sigma n would cancel this sigma n because it is in under the root, right? So sigma n it's in the numerator here, denominator here, and in the numerator here. So both sigma n that would cancel out, and our expression for the error probability can be rewritten as 1 over 2 pi e over sigma n to infinity e raised to the power minus y square over 2 dy. Now it is exactly in the form of q of x. It is exactly in the form of q of we say q of y, q of x, as I mentioned earlier. So I can rewrite this expression now in the form of, we can say this is exactly equal to q of e over sigma n. Now this is your E is the energy of the signal, sigma n is the noise variance, and we already derived this noise variance. We derived this noise variance to be equal to noise variance. We said that our noise variance is actually equal to n naught times E, right? So the standard deviation is square root n naught times E, right? So if you put this value, you can rewrite your Q, which is E over n naught times E, right? Or in other words, just simplify it using simple maths, right? So this is equal to Q times square root E over n naught E, right? So this is cancelled, and you are having Q of under the root E over n naught. Now your probability of error is actually Q of E over n naught, energy of the signal over noise power spectral density. E over n naught is actually known as the signal to noise ratio. So your E over n naught, is signal to noise ratio. So the higher SNR, if SNR is high, your probability of error is low, because Q of x is low, because this term Q of x is low. So the and if you try to plot this for different values of SNR, for orthogonal signals, if you plot for different values of SNR, you can get this plot for, if you have SNR over here, and you plot your curve, you will get a monotonically decreasing curve for orthogonal signals, which is Q function of the SNR. So your probability of error on the vertical axis and SNR on x-axis gives you a curve which is monotonically decreasing curve. So this is how you derive the expression for mathematical expression for for the bit error rate, or the probability of error of orthogonal signals, right? So if you have orthogonal signals, you can repeat all this process by assuming that S1 is transmitted, and you will come up with the same expression for the probability of error. Now I would like you people to do this, to repeat these analysis, and do it for other signaling scheme as well. This is just for orthogonal signaling scheme. If you have antipodal signals, if you have on-off keying in a binary signaling scheme, or you have M-array modulation scheme such as M-array QM, you can just find out the mathematical expression for the bit error rate, and that would be in the form of Q of x, right? So this is all about this bit error rate expression, the optimum receiver would give you this performance in the additive wide Gaussian noise in the presence of AWGN.